I will take you to a completely different area, and that is the area of Botswana, where in 2017 a earthquake, a magnitude 6.5 earthquake occurred. And what I will do in this presentation, I will take you through my journey that finally, I arrived at the question, well, rifting of the Kalahari Craton, well, that's a very provocative subtitle that I have deliberately chosen. But before I will take you along with my journey, I would like to first thank all the people listed at the top who installed the stations and the people at the bottom actually who did most of the scientific work. Okay, so first, Botswana. From the outside, I would like to say that Botswana is seismically not a very active country or region. There are only 4 magnitude 4.5, 4 to 4.5 earthquakes that occurred between 1990 and 2016. And these earthquakes, actually, they occurred in the northeast, let's say the Okavango Rift Zone. I'll come back to that later. So not much happening in Botswana until really out of the blue in 2000, or seemingly out of the blue, of course, a magnitude 6.5 occurred with aftershocks. And so this enigmatic earthquake, what was the cause of that? That's the question. Okay, so first, I'll give you an overview. This is a very schematic, rough overview of southern Africa with the Kalahari Craton, and that is usually taken as the combination of the Archean Zimbabwe Craton, the Archean Kapval Craton, and the Proterozoic Limpopo Belt in between. Okay. So those are the tectonic units that we are interested in. And before going into the seismological research, I'll just first show you actually why we put our seismic stations in Botswana. Well, Botswana is an area covered for a large part by Kalahari sands. And so there is not much direct geological evidence from the center towards the west. This figure also shows not only the Kalahari sands, which are in brown, but also, let's say, the branch of the southwestern branch of the East African rift system entering Botswana in the northeast. So if you want to know more about the subsurface of Botswana, you need to install, and let's say crustal and mantle structure, you need to install seismic stations. And before 2013, there were 2, let's say, broadband stations in Botswana. And we from Utrecht University, together with University of Twente, and not to forget Botswana Geo Institute, we deployed a temporary seismic network indicated by these blue triangles. The earthquake is at the location of the red star. Luckily, in 2018, the Botswana Geo Institute actually took over our instruments, and since 2018, it's therefore now the permanent Botswana seismic network. Okay, so using the data of those stations, first zooming in again on the tectonics. First I showed you the big overview, and now we go into a little bit more detail. Again, Zimbabwe Craton in light yellow now, Kapval Craton, and the Limpopo Belt in oranges-like colors, with an extension with the Magondi Belt towards the north. But this combination of Zimbabwe, Kapval, and Limpopo, that is called the Kalahari Craton, that was formed 2.7, 2.6 billion years ago. Okay. Well, let's first have a look with our seismic network, which events could be located. Well, let's start maybe with the events in the northeast, the red ones here, the colors indicate different sizes. There is the East African Rift Zone with the southwestern branch in the Okavango Rift Zone here. The big event, 2017, magnitude 6.5, with aftershocks, the different colors give the size of the events. And there are also two regions that are associated with diamond mining. The locations of these events are, and the number of events is much larger than determined previously, and that is because now we have such a dense network. Okay, but these are what we call absolute locations, and these absolute locations are just obtained by the data of our stations, but using the same data, but a different technique, and this different technique is based on the fact that the ray paths of two events which are very nearby towards a single seismic station are very similar, except for the difference between the two seismic events. So if we now use travel time differences between the two events, we can forget about all the velocity structure along the rest of the path, and we get much more accurate relative locations. So using this relative location technique, we can obtain, of course, much better relative locations. So this double difference technique then was applied to the data. And the top two figures actually are from Kolawole and others. Kolawole is now one of the organizers of this seminar. And so they show the model, and that is based on aeromagnetic data. And when Dagmar, my master student, actually plotted the event locations, and you see the event locations here indicated by the white circles. Actually, she found an amazing agreement with the fault which was inferred from the aeromagnetic data from the Moyabana fault. Actually, if you look at the location of the earthquake, this is the main event, moving upwards here to the in this direction, and there might even be an antithetic fault here, indicated by the seismicity, but that's maybe a little bit questionable. So this Moyabana fault is a normal fault in a thrust fault system, and in map view, here it's a map view, we copied this part of Kolawole's map, and the Moyabana fault is shown here. And again, an amazing agreement along the Moyabana fault towards the main shock, and then with the aftershocks towards the northwest. Okay, so the events are along the Moyabana fault, close to the boundary of the Kalahari Craton in the south, and the Limpopo belt more towards the north. Okay, and as already shown in the previous figure, and also in this figure, actually from the data that we recorded, we could not only infer the focal mechanisms, and the focal mechanisms are shown here, and they show northwest, southeast strike of all the events. Here. They align with the Moyabana fault here, or the transition from the Kalahari Craton to the Limpopo belt. But moreover, using the waveform modeling, and here of the 6 largest events, and this is just one overlay of the seismic data with the modeled data, we could also quite accurately now determine the depth of the events, and that is using surface reflected data. And what we
You're
found,
at 10 minutes.
yes, perfect, thank you. What we found is that the main shock occurred at 29 kilometers, and these aftershocks from 21 to 28 kilometers, so they were all shallower and towards the northwest. Okay, so 29 kilometers is really deep, but actually for the cratonic area in southern Africa, it is not uncommon because all the yellow and red dots in this figure from Craig and others, they show all the events at 20 to 30 kilometers depth. So, is the event in the crust or in the mantle? Therefore, we rely on the data, on the results of Islam van Del and others, and they inferred the crustal thickness based on receiver functions. Well, I won't go in all the details, but beneath all these stations around the earthquake location, we see that the crustal depth is around 40 kilometers, indicated by the yellow color. So the main event and the aftershocks occurred in the lower crust, not in the mantle. But if you believe the strength profile or typical strength profile like this, then brittle failure only occurs, let's say, in the top 20 kilometers or so, and there should be a ductile behavior below. However, so that was a puzzle to me. So I thought, well, how can we have relatively deep crustal earthquakes? Well, it has been shown that if you have a dry crust with dry lower crustal minerals, they can be metamorphically metastable. And then if you have a tiny amount of fluid, then it can cause the transformation to eclogite. And this is also called transformational faulting. It just behaves like an earthquake, but it is actually a phase transformation. There is field evidence for that from the Caledonian granulite in Norway. Alstrom in 1987 was the first to detect that, and there are many more studies since then. But also Proterozoic gabbros in Zambia. There have been lab experiments that showed acoustic emissions, and there are also petrological and geophysical models, mostly for the Himalayas, but also for Norway, that show that such a mechanism is feasible. Okay, so now let's assume that this earthquake occurred in the dry metastable lower crust, but then that would only occur if there would be fluids. So is there any evidence for fluids? Okay, again, a study from Islam van Del and others using surface wave tomography. And here we see different depth levels from 5 to 200 kilometers here at the top left, top right, with low seismic velocities in the northeast, Okavango Rift Zone, high seismic velocities beneath the Kalahari Craton very clearly. And if we now move up to a depth of 40 kilometers, then again we see high seismic velocities in the Kalahari Craton, but low velocities in the Limpopo belt and to the north. So now, if we take a cross section from north to south, north here, the low seismic velocities associated with the Okavango Rift Zone, the high seismic velocities of the Kalahari Craton, then we see low velocities here. And if you wish, you can interpret that these low velocities at the base of the crust and the uppermost mantle might be associated with melts and or fluids moving from the, let's say, the plume beneath the East African Rift Zone towards the location of the event. So that's the interpretation, and that's a hypothesis. So could there be melt and fluid transport from the southwestern branch of the East African Rift Zone? That brings me to the hypothesis, I admit, a speculative hypothesis that essentially says, well, potentially there is, from the mantle plume to earthquakes in the Kalahari Craton, the mantle plume, like shown here, produces upward mantle flow. It produces extensional stresses in the lithosphere, so normal faulting, and it also creates decompression melting. So these melts with the fluids then locally alter the lithospheric mantle beneath the crust, and this mantle is then metasomatized. Actually, there's evidence for metasomatized lithospheric mantle from xenoliths, and so, I mean, it does appear to happen. Then the fluids, they migrate along this crustal Kapfau Limpopo suture, where eclogitization takes place of the dry metastable lower crystal minerals, and that produces the main shock, and the aftershocks are then produced by further upward fluid migration along the pre-existing fault or faults. So that brings me that potentially the Kalahari Craton will break up along the Kapfau Limpopo suture, and maybe in the very, very future, rifting might occur, of course, but everything depends how this eclogit, well, this area, whether that will behave weakly or whether that will behave strongly. So actually, it's still a question to me whether there will be rifting of the Kalahari Craton. And there I would like to thank everybody, the audience, but also in particular those men who installed the seismic stations and made this research possible. Thank you for your attention.
Thank you very much, Hanneke. I can see immediately that Fula has a question.
Hi, Hanneke. That's a very nice talk, and it's exciting hearing you present the work. I really enjoyed reading the paper. So on the role of fluids, I think there is evidence from the magnetic data itself that that particular fault zone is altered. It does not have the same character as the basement blocks around it, and it seems like a long-lived zone of fluid alteration in the crust, if I think about it from the perspective of magnetic expression of fault zones. But the question I have, is primarily related to the result from seismic imaging that you showing low velocity anomalies. Yeah, right here. So this region has experienced a lot of volcanism in the Mesozoic during the Karoo, and I've seen this basalt in the field across this region myself. And I'm wondering if this low velocity anomalies could be related to this. And the reason is because at the surface, we don't see active. We know the fault is active and it's probably slow moving. It's not deforming the surface, but there's no evidence of active fluid activity, crustal fluids upwelling at this location. So I wonder if this anomaly here is related to some ancient activity and not necessarily present day. I want to know what you think about that.
Yeah. That's a very good question, and I have looked very carefully, particularly, let's say, at the locations of the Karoo volcanics, and I mean, it has been. So I've been thinking about that, but I don't see actually any evidence in this particular region. In other regions, yes, but here not. Actually, what I had hoped is maybe to see evidence for, in the crust and in the mantle, seismic evidence for the different tectonic areas. And I haven't seen that. What I do see is, particularly in this figure, you see it really very well, that this is really the border. I mean, this is the Kapfau Craton, and it is really at the border of the Kapfau Craton. And I don't see, So that's, I've been thinking, but I mean, you might be right, but in the seismic data, the seismic models, we don't see any evidence for that. So that's the reason why I think, okay, maybe it comes from the north rather than from, let's say, the east.
Thank you.